Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Bradley Hutchinson and Caty Pilachowski with us today. Hello, Bradley. Hello, Caty.
Hi,
Hello.
everyone.
Let's see. Bradley, let's start with you. What's your geolocation? Where are you at?
Bloomington, Indiana.
Oh, we're in the heartland. All right, very good. And let's see. Well, we're past solstice, barely. So the days are starting to get longer. So do we have snow on the ground in Bloomington?
Kind of. I
Kind
mean,
of.
it's very weird because it was like 68 degrees yesterday, and now it's 17 degrees. And
Ooh,
so it's
ooh,
very
ooh.
strange
Oh
and
yes,
windy.
it's that Midwest swings, right? And if you don't
Yeah.
like the weather, just wait a day or two. Very cool. Very good. And Bradley, what is your position there in Bloomington?
I'm a student, undergraduate student, so I'm in my final year of undergrad.
Awesome. Congratulations. Very good. And Katie, I imagine you're in Bloomington as well.
Exactly. Geolocated right here in the heartland. It's freezing outside. We have lost all of our leaves. It's gray and cloudy, very windy. And the wind chill is appalling today.
And I will
These,
mention that.
these are unusual days for Bloomington. We're usually much milder than this.
Okay, okay. Unusual days everywhere.
Yeah. Looking forward to
Let,
Phoenix.
let's see, and I'll be honest here. So I guess it was around Halloween that I did visit Bloomington, and we did run a peer review workshop there in Bloomington, Indiana. And it was the trees were already turning colors. I got a great shot of some red leaves. It was really lovely. Very good. Let's see, and I am in Phoenix, Arizona on this December 30th as we record this, and we are definitely in our winter mode, but we don't get quite the swings as the Heartland does. So we'll start off in, maybe the 40s, mid 40s or so in the morning, and it'll warm up to a very lovely 70 or so. So yes, we got all the snowbirds coming down. Very cool. And Bradley, what do you like to do for research?
So, in relevance to what we're talking about today, I'll probably just say that I like to do machine learning. I love machine learning, and applications of machine learning to astronomical data sets.
Cool. Very good. It's a happening topic these days.
Yeah.
And Katie, what do you like to do for research?
So I'm the stellar spectroscopist. I love stars and figuring out their characteristics, their abundances, their role in the Milky Way, um, the the galactic chemical evolution of the Milky Way. All of that is wonderful. And that's why Bradley and I make a good team because I bring the stars knowledge and he brings the machine learning.
Great partnership. Great partnership. And that is going to bring us to this very awesome AJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. A wavelength-aware, unsupervised learning approach for large, multicolor photometric surveys. And Bradley and Katie, take us away.
Awesome. So I'll probably start by mentioning my awesome co-authors, my awesome supervisors,
Good.
and a little bit about how we met. So
Yeah.
I also do research within the ALICE experiment at CERN,
Okay.
and I went to a machine learning training at LBNL a few years ago.
Uh-huh.
And then I was very interested in doing astronomy research, and I wanted to apply this machine learning that I just learned. And so I went to Caty and talked to her about it. And we came up with this project, and it was originally with the Blanco de Cam Bulge survey.
Okay.
Um, and so that's also how Christian got involved, because Christian is
Hmm.
a big proponent of that. And the issue that we face is that I was trying all of these machine learning methods and models,
Maybe.
um, to a very complicated data set, an extremely complicated data set, which is the galactic bulge.
Yes.
And reddening is a huge issue. It's very complicated. And so if we were wanting to make a paper that showed like a proof of concept, we probably wanted to first apply it to a data set that's a little more simple.
There we
And
go.
that's how we got to pan-stars.
Uh-huh. Good. Okay.
Awesome.
Cool. Love the backstory. That's great. All right. Good shout out. And let's go.
Awesome. So yeah. So basically we have been in this era, I believe, of big data in astronomy for like a few decades now, right? With SDSS and 2MASS,
Mm-hmm.
pan-STARRS. But recently, it's scaling up very largely, like with LSST, like the 10 to 20 terabyte nightly data collection.
Yes.
And so this provokes this critical need for new methodologies
Mm-hmm.
in order to analyze all of this data. And a good way to put it is to find the gems in the big data,
There
right?
you
The rare stuff.
go.
So that's mainly what we're focused on. And so machine learning has become a very good tool, right, to try to solve this challenge. And it's been used quite a bit recently in astronomy. A lot of people are using it,
Indeed.
particularly like convolutional neural networks.
Mm-hmm.
Long short-term memory has been used, which we'll talk about later. But it's mainly been used in time series data. It's very good for light curves. And then autoencoders have also been used to like denoise
Yes.
diffuse
Yes.
radio sources.
Mm-hmm. Cool. Mm-hmm.
And so now it is like within this context that we will talk about our application of a long short-term memory autoencoder
Cool.
for multiband photometry. And so the goal is to distill the 5-band photometry into a 2-dimensional latent space, which you can use for easier analysis,
Okay.
and then it will reconstruct it back to 5 dimensions,
Okay.
which you can then use for anomaly detection.
Ah,
Yeah.
yes. Mm-hmm. Looking for those gems.
Yes, exactly.
Mm-hmm. Okay, I'm with you. Mm-hmm.
Awesome. So I think we could probably go to the next section.
Okay.
Perfect data selection.
Yay.
Um, the fun stuff. Yeah, so also a little bit more backstory is that the data sets that I have used, I've used 2MASS, BDBS, SDSS, and
Uh-huh.
then but eventually we settled on pan-STARRS. And the big reason for this is that it offers a catalog for source types based on probabilities.
Okay.
And it's called PS1 Stream. It
Mm-hmm.
allows us to easily remove non-stellar objects. So that was a big problem we had.
Yes.
Typically, when I was using SDSS, was
Yes.
a lot of contamination.
Just gets everything. Yes. Mm-hmm.
Yes. And so that is why we use pan-STARRS.
Mm-hmm.
And also, the photometry is incredibly clean. Like very impressive photometry.
Okay.
Uh,
GMR. Mm-hmm.
and so we also choose a field between 60 and 80 galactic latitude.
Mm-hmm.
And so it's basically an annulus around the North Galactic Cap,
Uh-huh.
which is way better than the
Bulge.
galactic bulge, right? Like in terms of reddening.
Right. Exactly.
And it's also handful to a few globular clusters. And so
Mm-hmm.
big purpose for that is in the latent space, if we're working with unlabeled data, right? We need to be able to understand what this latent space is doing. And a big way to do that is to remove the distance luminosity degeneracy,
Okay.
like in a CMD,
Mm-hmm.
and see what the latent space is doing.
Okay. Mm-hmm.
Awesome.
Yeah.
And then, so we also make a series of cuts, very basic ones, like the
Mm-hmm.
probability of a star has to be greater than or equal to 99%. But just to note, we also take stars that are within, I think, 0.15 of a degree of the center of our globular clusters that have a probability of it being a star greater than or equal to 70%.
Okay.
Because if you do the 99%, then you cut off the main sequence turnoff for a lot of our stars in the
Right.
globular cluster.
And we do want those.
Yes.
Yeah.
So it's just basic color cuts, and errors in the mean photometry, which is 0.05, which will become important later.
Mm-hmm.
And
Good.
so, and also as an important note, I want to mention that the model is being trained on real observational data.
Yes.
And so we're not doing anything like building a denoising autoencoder, like I say in the bullet point number 6, is that you can build a denoising autoencoder and manually introduce noise
Yes.
to see how the model performs.
Yes.
But we can't really do that in our case because we are using real astronomical data that is already noisy, right? And so adding noise onto noise to me, it doesn't make a whole lot of sense.
Right. Okay. Very good. I'm with you.
Awesome. So we end up with about 3 million stars with
Mhm.
precise Grizzly photometry, which we define precise as meeting the cuts above.
Uh-huh.
And then we also match to Gaia
Mm. Good.
using like a no neighbor cut. So if there are 2 stars within this radius, then you take none of them.
Right.
And then we also match
Yeah.
to Sinbad.
Okay.
So to talk about this a little, it is basically what we're trying to show is that since we have been in this era of big data for a while now, and it's scaling up hugely now, but the whole goal is when you do these all sky surveys, you have these subsets of data which are labeled, right? And even though the model that will be trained, it'll be trained on unlabeled data, and the model can freely explore that data.
Right.
In order to understand things like the latent space or what the model is doing, it's very important to use those labeled subsets that you have.
Right.
Right. And so we're grabbing all of these subsets to use to our advantage later to
Good.
further understand what the model is capable of.
Mm-hmm. Mm-hmm. Okay, very good. I am with you. All right.
Awesome. Perfect. So let me move there we go. So now I guess we'll talk about, could you please scroll up just a little more?
Nope, there we go.
Oh, there we go. I didn't want to forget to say this about the de-reddening.
Oh, yes, absolutely.
It's a bit
Even
big.
though we're in the North Galactic pole.
Yes. So we still do de-redden. And extinction coefficient of 3.1 is used, or the standard extinction law. And then the corrections end up being very small. So the last sentence shows how small they are. So 9.99 to the -2, that's,
Oh, yeah.
I believe, 0.3 magnitudes at most. It would change the photometry in the G band. The G band would be affected the most.
Yes.
But these corrections are very tiny, right? The mean value is 1.89.
That's great. Good,
Perfect.
good.
So now we have our data set of 3 million stars that are de-reddened, and we also have subsets. And so we're really ready to go now.
All right. Very good.
Awesome. So it's machine learning time now. Now it's time to talk about machine learning. And so basically, the shape of a star's spectral energy distribution, right? And I guess I'll just read this because this is the very important paragraph. I won't read it word for word, but this is a very important paragraph.
Yes.
And along with the wavelengths and strengths of various absorption and emission line, encodes information about its atmospheric properties, such as temperature, surface gravity, and metallicity. And things also change that, like the opacity of a star. Anyways,
Yes, they do.
the important part is that these physical properties can be extracted from an SED using the relative flux measurements of a star when viewed through filters, having different effective wavelength regions.
There you go.
And the changes in the brightness over the bands in the steepness, which is the colors, are very important and deeply related to the underlying physical processes happening in the star.
Okay.
And so it motivates the use of what we call a wavelength-aware model that can adaptively emphasize specific passbands. So if you could please go to figure 1.
I'd be delighted to go to figure 1. All right, figure 1, SEDs.
Awesome. So this is of our subset, our Sinbad subset of different types of stars. You show, I basically on the x-axis put the bands in wavelength order, right? Because it shows that
Grizzy.
The multiband photometry, it's not completely independent of each other. They are related together as tracers of the underlying spectral energy distribution.
Yes.
And so this is the the big idea of highlighting a wavelength-aware model is that it's also very important that depending on what kind of star you have and what properties that star has, certain photometric bands possess more information than others. Certain color indices possess more than others. Like with brown dwarfs, you would be more likely to use JH and K, look at JH and K rather than say G and R.
Yes. Yes. Okay, I'm with you. Yeah. Okay, got it.
Awesome. Oh, and then just to so the listeners don't get confused, I would say it's normalized to the G band. So that's what the y-axis is doing. So everything starts at 0 in G, and then you're basically looking at G minus R, then G minus I. But the whole point is you're looking at the shape and showing that it's tracing the underlying spectral energy distribution of the star.
Very cool. Very cool. Well, let me ask one question while we're here. Any worry about binaries?
In what aspect?
Are they
Just
in
in
the
general?
are they in the set, or have you
Yes,
filtered
there
them
are a
out?
lot of there are a lot of binaries in the set. Yes.
Okay.
And so we'll actually talk about this later.
Okay.
About how it can affect anomalies and things like that.
Good. Okay. I'm with you.
Perfect. And then if you could please scroll back up to the previous page. Just I think the bottom part. Oh, perfect. Yes, to talk about the long short-term memory. Awesome. So now we get into LSTM network.
Yes.
And so LSTM networks are a variant of recurrent neural networks, but it addresses the challenge of learning long-term dependencies. And so the big thing that I want to get across in this talk is we are using LSTM networks in a very non-traditional way. So when people hear LSTMs, they automatically think time series and things are ordered. Yes.
Yeah.
But we are not doing that. We are not doing that at all. So what you'll see later is we feed the model the entire photometric vector at once, and it has a time step of 1.
Okay.
But I'll show in a minute how we can still use all of the components of an LSTM to our advantage to solve this problem.
Okay.
And the biggest way that we do that is by using the memory cells that they have. And so I see trying to figure out how much time we have to make sure I get through everything
that you want to.
But the important part is that things like the cell state carries information through the sequence of inputs. We're not. I will mention that again later because the sequence of inputs is different for us. But the important part is the gating mechanisms, and that determines what information to add, remove, or retain in order to minimize the loss function, which you'll see in a second. We use mean square error.
Yeah. Okay.
Yes.
Yes.
And so here is just a very simple description of what each of the gates do. There's an input gate, a forget gate, and an output gate, right? So basically, what new information is significant enough to be incorporated? What is not that important anymore, right? What is irrelevant? And then the output is it dictates what part of the cell state should contribute to the output at each time step. And so we also formulate that mathematically. And so we see a lot of things drop out because our time step is 1.
Right.
Oh, and also to mention what you see here in the input forget and output gates, those are sigmoid activation functions. And so it inputs a value between 0 and 1, which corresponds to either blocking or allowing information
There you go.
to pass through that gate.
Good. Good. Okay. Yep.
Awesome. And then, so the candidate cell state uses the hyperbolic tangent activation, which is what is described in the original paper. But we manually tested that, and I'll get to that later, but it did not work for us. It did, if you look at the the reconstruction between like the reconstructed magnitude, the difference between a reconstructed magnitude and the original magnitude,
Okay.
it would do some very oscillatory behavior.
Eek.
Yes, something we do not want at all.
Well, maybe they're pulsators. I don't know. But I doubted it. Probably the amplitude you were seeing.
It would be like at 16th magnitude, it would overpredict by a magnitude.
Ooh.
And then at 17th magnitude, it would underpredict by a magnitude, right?
Yeah.
So that's why we end up changing that to the ELU activation function.
Okay.
Awesome. So if you please go to the top of the page on the right.
Uh-huh.
Oh yeah, this is the good stuff.
Okay. I like good stuff. Okay.
Awesome. So this is the important part. In our case, we do not unroll the network across passbands.
Okay.
And so it's processing the 5 magnitudes jointly in a single time step, which makes these features go to 0. And that term vanishes. And the input and output gates become functions of the entire photometric vector.
Yes.
And so the equations are very important because you see the element-wise multiplication in that basically if you look at the first hidden state, right, from the 5-dimensional photometric vector to the first hidden layer is that it takes into account every single photometric band for every single star.
Yes.
So on a star-by-star basis, the model is able to determine which bands are more important than others on a star-by-star basis, which is something like a traditional feed-forward network could not do.
Cool. Very cool.
Awesome. Okay. And so the primary advantages is what I just said was I said in I maybe a little bit of a less professional or scientific way, but it computes input dependent per sample reweighting, and it can emphasize the most important wavelength regions. And so for an example to show this, you say a white dwarf would tend to upweight blue sensitive features that are driven by the bluer bands like G and R, and it would downweight the redder bands, while a cool main sequence star will shift its weights towards I and Y.
That makes sense.
Which is also very important because when you're working with these all-sky surveys, the photometric data sets are heavily imbalanced, right? Dominated by a main sequence majority.
Sure.
And so also you can even take rare stars, for example, like a blue straggler, right? And high weights would be assigned to both the blue and red ends. So it could capture the entire SED shape. Awesome. And then the second one is that photometric data is susceptible to noise. We're working with real observational data. The noise is present.
Yep.
It is minimal, but it is present. But the important part is the gating mechanisms allow the LSTM to learn what information is important to retain and what information is not. So it makes it robust to noise.
Good.
Awesome. And so the last part is that I spent all this time talking about long short-term memory. But if you use that in a standard like neural network, what's a good way to say this? A supervised method, if you try to use this we do not have labels.
Right. Stars don't have labels.
Exactly, right? We don't
which is a bit unfortunate.
For our 3 million stars, we don't know which ones are exactly main sequence and things like that. And so this provokes the need for an unsupervised machine learning method.
Yep.
Right. To have a model that can operate freely without labels, to freely explore the data set. Cool. And so this is how we get to autoencoders.
Yep.
Awesome. So autoencoders, again, it's unsupervised learning technique that efficiently encodes data for dimensionality reduction.
Yes.
And then decodes it, right? And this is what I was talking about earlier that we use to detect anomalies.
Yes.
And it consists of 2 main components, an encoder and a decoder. And so what I was talking about is you take the photometric vector and then it will reduce its dimensionality to what we call this lower dimensional space, which we call the latent space. And then from that latent space, it will reconstruct it back to the 5 dimensions.
I'm with you.
And then it regulates itself based off, well, what we choose the mean squared error between the reconstructed value in the input value.
Cool. Mm-hmm. Mm-hmm.
Awesome. Yes. And the objective is to discover a compressed yet informative representation of the data through the minimization of the loss function, which I just mentioned.
Okay.
Perfect. And it's important in the context of large observational surveys, because it can distill the complex nonlinear relationships present in the data set into a more manageable form.
Yes.
So this is one of the big important parts of the paper is that the data is getting so large and so complex. Traditional techniques of like analyzing color plots are getting more and more complicated, right? With that amount of data that you have. And you might, a big part of it is you might be losing information when you are analyzing using color plots because you're only choosing some parts of like the spectral energy distribution to look at. As to where if we have this machine learning model here that has to reconstruct all magnitudes, it thus has to reconstruct all colors and basically the underlying spectrum, the underlying shape of the spectral energy distribution.
Cool.
Right? So the loss of information is much less compared to a traditional technique.
Yes, very good. I'm with you.
Awesome. And so I keep going. Yes. Now we're here. Now we're here. We finally made it. The long short-term memory autoencoder. So basically, we got the long short-term memory with all the advantages that we say that it has for multiband photometry. But the problem is we don't have labels. So then we grab an autoencoder and then we put them together.
Lovely.
And this is how we get here. Here, let me move my camera. And so, yes. And so I don't want to repeat what I've said probably like 10 times about it taking the photometry and encoding it into a lower dimensional space.
Right. We go from the full to 2 and then back out to 5.
Yes. And so there's a handful of advantages. One, it's unsupervised learning, right? So we can operate freely. And this is important because it can potentially uncover new insights into stellar phenomena. Like, for example, if you have like a supervised machine learning method where you're going to classify if a star is a main sequence star or a white dwarf, when you do that and you build your labeled set, you have to make choices of how you're defining what a main sequence star is. And you could be biasing the model to classify something that it's really not. It could be something different, right?
Yes.
And so this allows the model to freely explore the data.
Yep.
Pattern recognition, I think that's a pretty obvious one with machine learning methods.
That's what it does best.
Then we already talked about dimensionality reduction and anomaly detection, how it does that.
Yep.
And denoising is a thing I've also said a few times, is it's trained on real observational data. And so it introduced natural perturbations in the training set. And you're also contracting from a higher input space to a lower input space. Because when you do that, it is now impossible for the model to learn the identity function.
Yeah, itself. Yes.
Yes, it can't just learn itself. And so it's pushing the model to learn a robust representation of your data set.
Beautiful. Beautiful.
And so it could support denoising. Is this fifth bullet point is the big ones.
Cool.
Awesome. So now model. So we use Keras, which is a high-level API for TensorFlow, which is the open library. And the biggest reason we do this is because, well, like we're astronomers, right? We're not computer scientists. And so if these big open libraries already exist, it's in our best interest to use them. It makes it very easy to build the models, right? This is a thing that I didn't mention earlier, but in this entire project, right, the difficulty doesn't lie in building the models. The difficulty lies in finding the right model, right, for your data.
Yes. Don't use a hammer for everything.
Exactly, exactly.
Okay. Mm-hmm.
Oh, and then also to mention the appendix, thank you for highlighting that, is that we have the code in the appendix, and then we also have a lot of anomalies in the appendix,
Cool.
which we'll get to later. Awesome. And so we pre-process the data, and it is very good practice to have the data scaled near zero.
Uh-huh.
Um,
Because we're going to be doing
but this is a little bit
3D%. Mm-hmm.
different than like the work I do in high energy physics of like me training a model in high energy physics, and you have like the transverse momentum
Yes.
and the eta and phi, like values between minus pi and pi is way different than it being 800 GeV. Like the orders of magnitude um, are way different. But in our case, in photometry, right, it's all the same order of magnitude, right?
Mm-hmm.
It's all between, I think, 15 and 22, right? So
Fair
we
enough.
just simply divide everything by 10. It's a
Okay.
much easier way of scaling than like using min-max scalar
Oh, yeah.
or standard scalar.
Yes. Okay. So now we've got a regularized set, and away we go.
Perfect. So I think I kind of already mentioned this, so I might not go into a lot of detail,
Okay.
but basically we formulate the architecture in a way that can be used with a multitude of surveys. Right. So we're formulating it with like n number of bands or n number of nodes
Mhm.
uh, to really show like this is not just for pan stars, right?
Oh,
It could be
sure. Yeah,
something
yeah.
like LSST, um,
We'll get to
something
that.
like that. And it's the same thing of the five. So basically it goes 5, 4, 3, 2, which is your latent space, and then from 2 to 3, 4, 5.
Yes. Hmm. Okay.
Awesome. And so this is the important part that I want to show is that if you could highlight the very last sentence of the paragraph, please. The resulting hidden in cell states in the encoder are
Uh-huh.
passed here. Yes. So this is a very important part of using the LSTM model
Right.
because it shows that every aspect of the model we are using, right?
Mhm.
So like the hidden in cell states from the encoder that
Yes.
are being computed
Yes.
are not just like not being used or being thrown away, right? They're being passed to the decoder.
Yes.
It's sort of mirror structure,
Uh-huh.
and it allows the model to quickly learn the mapping from the latent space to the reconstructed magnitudes.
Uh-huh.
So it's in, instead of looking at it as
Good.
if you didn't pass these things, then you basically could view it like you have a neural network going from 5 dimensions to 2 dimensions, right?
Mm-hmm.
But then the rest of the layers need to learn the reconstruction back to 5 dimensions from solely the latent space, right? It's starting fresh, basically.
Yes.
Um, and
Uh-huh.
so when you pass these hidden in cell states, you're giving it a huge advantage that it doesn't need to start over.
Right.
Yes.
Because we started with that. Right. I'm with you. I'm with you. Mhm.
Awesome. And the stuff I already mentioned, using an exponential linear unit. And then we
Mhm.
also do things like early stopping. And so it's to prevent overfitting. So it's
Ah, right.
right. You don't basically we let the model run and run and run. And then once it starts getting worse, then you kill it. That's
Yeah, yeah,
basically
yeah, yeah. Okay. Uh-huh.
um,
Uh-huh.
what you're doing. And then ooh,
Uh-huh.
and then I don't think I mentioned this with the training and validation test splits is that it's a random grab of data.
Okay.
Uh,
Okay.
and so this is important because I had to do a lot of thinking about this. Oh, and also how computationally expensive it is. Like if I wanted to grab a selection of my data that is representative of the entire data set,
Okay.
um, you need to be very careful, right? Because so a way you could do this is to make like little squares, right? Of like, say you take two color indices, right? And you want to grab X amount of stars from each little square
Hmm.
uh, in order to get a well-represented population in your training set.
Okay.
But the problem is that that becomes very computationally expensive.
Squared.
Yes. And so we simply take the method of randomly grabbing a large population of stars.
Okay.
Um, and you can justify that is, well, first we grab a large population. So it's not like we're grabbing like 20,000, like we're grabbing like a million, over a million.
Okay.
Um, and two is the claim of the model that we are using, the models that we are using specifically alleviate the problem of certain populations dominating in the data set.
Okay. So equal representation, shall we say?
Yes. Yes. So I just wanted to mention that I think that's a pretty important part.
Oh yeah. On the training, sure. Mm-hmm. Mm-hmm.
And so the just a little bit of our hyperparameters. We did a little bit of a manual search, not a huge manual search. Um, I mean, the problem, it seems, is that like with neural networks, there are always more knobs to turn, it feels like, right? You're trying to try so hard and spend so many resources to get this perfectly optimized thing.
Mm-hmm.
But we did a little bit of a manual search,
Okay. Fair enough.
and are happy with the completely content with the results that we got.
Okay. Good. Okay. I think we'll cover that there. No.
Perfect. How am
Okay.
I doing on time? Oh, it's already 12:50.
You're rolling. Let's put it that way. You're rolling. It's all good. It's all good.
Okay. Awesome. Perfect.
Okay.
So I guess I'll start with figure two.
Yeah.
So we run the model 5 times with
Okay.
completely different weight initializations each
Ah,
time.
okay.
And that's the important part. And that's why you see such
Yep.
different results
Mm-hmm.
in each of the 5 runs. And then the black lines
Uh-huh.
are a standard autoencoder.
Okay.
And so this is showing that by adding the LSTM units to the autoencoder,
Yes.
you are getting much better performance, like up to an order of magnitude
Yes.
lower loss.
Yes.
Uh,
Get out. Yes. Uh-huh. I'm
and
with
so it
you.
motivates the use of this model
Uh-huh.
compared to a standard autoencoder.
Good.
Shows that the gating mechanisms are working in our favor, right? There's
Correct. Yes.
awesome.
Very good. Okay.
Probably figure three, probably the next figure.
Okay. Figure
We'll
3.
probably just start flying through figures now. Like we'll probably just be focusing mainly on figures now.
Okay. All good. All good. Okay. There we go. Latent spaces.
Awesome. So the reason I showed the loss function first, the loss figure first, is
Uh-huh.
that I wanted the reader and the audience to believe that the latent representation, right, the manifold that it's learned
Yes.
is robust, right?
Okay.
And it
Okay.
represents
Sure.
um, something, or it represents something very meaningful in the sense that from this two-dimensional space, it can reconstruct the photometry extremely well.
Very good. Okay. Mm-hmm.
Perfect. And so this is the talking about the different weight initializations and just showing that we are not forcing the model in any way to say
Mm-hmm.
like learn a specific shape or like a manifold.
Sure.
And so the shapes that you can get, the learned representations can be very different. And then you see in these five. And so
Mm-hmm.
when you pick the five, when you have these five, you need to pick which one you want to use. And so if I
Yes.
think the next thing is a table,
Okay.
scroll down.
Let's see. Table 1. Here we go.
Oh, there we go. Awesome. So this is the important part. So for each of these 5 runs, we have the training loss, the validation loss, and the
Yeah.
test loss.
Okay. Yep. Mm-hmm. Yeah.
And so the important part becomes when you're choosing what model you want to use,
Mm-hmm. So,
do you want to use your latent space, right, to do analysis?
uh-huh.
Or do you solely just care about getting the best reconstruction possible?
Okay.
And so if you only care about reconstruction, then you would use the latent space which with the lowest loss, and you
Yes.
don't care about what shape
It
it's
is.
taking.
Yes.
Um, but for us in this paper, we
Mm-hmm. Sure.
we say that it's important for us, right? Because we want to see what this embedding of the photometry looks like, right? And what we can do with it. And so we choose model 5 here.
Mm-hmm.
So you see the training loss is not the lowest training loss
No.
compared to run 4 and run 3.
Uh-huh.
But if you scroll up just a little, it has the most clear global structure
Yeah.
out of any of the spaces. And so that's why we choose it.
Yes. Okay. Okay. Mm-hmm. I'm with you.
Perfect. Awesome. I think we can go to the next figure now.
Okay. Table 1. These are going to be differences. Mm-hmm.
Ooh. Okay.
Or you can go to
Could
somewhere
you
else if you like.
could you please scroll up just a little? I forgot that that's the
Table 1.
awesome. Perfect. Right here.
Okay.
Perfect. And so for reconstruction, we're defining this reconstruction as a metric that measures the discrepancy between the input magnitude and the reconstructed magnitude that's predicted by the model.
Yes.
And so table 2
Mhm.
shows how many stars are predicted beyond a certain magnitude threshold. That's table 1. But um let's see. The important part is that I wanted to show that the percentage of stars with 0.01 uncertainty or less in their observed magnitude
Uh-huh.
is 53%, 74%, 92%, 84%, and 57%.
Okay.
If you compare this with table 2, if you could please scroll down a little,
Sure. Let's
is
slide
that the
to table.
LSTMAE, oh, where is it? Okay, there we go. Let's see.
Yeah. I'm with you.
If you look at the 0.01, it predicts
Mm-hmm.
a larger portion of the data set, percentage of
Yeah.
data set within
Okay.
0.01 magnitudes.
Okay.
And so
Yes.
this is
Right.
what
Right.
motivated us to look into the potential of it denoising.
Yes.
Um,
Hmm.
so if you could please scroll up to
Yeah.
now I'll go to the figures. That's the
Yeah. Um, with you on this one. Okay. Mm-hmm. Let's see. So you want differences?
yeah, these guys. Perfect. Figures 4, 5, and 6.
Mm-hmm.
And so the M minus M prime that you see here
Let's look at this
is
one.
the reconstruction metric that I'm talking about, right? It's the
Yes.
difference between the observed magnitude and the reconstructed magnitude.
Yes.
And I spent an outrageous amount of time figuring out how to get this how to make this plot, like the colors, to color them by the different bands in a hex bin plot and make them all different.
Uh-huh. Well, you
But
did
it's
it, so
cool.
congratulations.
Yes, I did achieve it. But anyways, in this first one, what I wanted to show here is
Uh-huh.
that if you look at the reconstruction metric versus apparent magnitude, there is not a trend in which as the source gets fainter, right,
Uh-huh.
the model's
Uh-huh.
predictions are not spreading out or getting worse in a lot of bands.
Correctamundo. Right. Pretty even all the way
Like
across. Uh-huh.
the only one where it's a little suspicious is the I band. The
Yeah.
I band is the big one, and maybe the Z band. Um,
Mhm. A little wider, but yeah.
yeah. So if you scroll just a little down to figure 5, this is the
Yeah. Just wanted to focus on one here. Oh, here we go.
this is the uncertainty in the measurement versus the apparent magnitude, right? And this is what
Yeah.
we would expect is that as the source gets fainter, right? the uncertainty in the
Things
measurement
get
gets
larger.
larger.
Yes.
But we're
Mm-hmm.
saying that the model's predictions are not changing, right? As the source
Yeah.
gets fainter.
Very good. Very good.
So if you go to the figure 6 now,
Beautiful. Okay, and this one is differences. Okay. Okay.
awesome. So this is basically just me wanting to show the correlation between the uncertainty in the measurement for each band and the reconstruction metric, right? And you see here is the correlation is very tiny. It's
Right.
very tiny. The only one where you can
Right.
see it increasing is the I band,
Mm-hmm.
and maybe the Z band a little, but
Mm-hmm.
especially for G and R and Y, the correlation is essentially zero.
Flat. Yep.
Uh,
Mm-hmm.
which is this is us showing
Yeah.
the support for that it's potentially denoising. And so it requires future analysis to truly understand if we are improving the quality of measurements or not.
Okay. We'll come back to that too. Okay.
Perfect. So I think we could probably go to the next figure now, is the
Okay.
oh yes, this is a good one. This is a good one.
Histograms.
Histograms.
Reconstructions. Okay.
Perfect. So this is me just showing a bunch of different color indices. Actually, I go in order of like G, R, I, Z, Y, and then I show like the big broad colors of like G minus I or I minus Y.
Okay. I'm with you.
And it's just to show
Pretty
the
good.
complex distributions that
Mm-hmm.
the model is reconstructing.
Mm-hmm.
And reconstructing very well. So just to be clear, like the plot is in log scale.
Mm-hmm.
So if you look at I minus Z,
For example. Okay.
and you see on the very left end, it's like, wow, the model is doing terribly. That's 10 stars, right? That's
Yeah.
right. We have a data set of 3 million and it's 10 stars. And it's also, excuse me, it's not very bad because it's showing that
Generally.
these guys will appear as anomalies,
Right.
right?
Mm-hmm.
These guys are anomalies, which makes sense. You would want the things with the most extreme colors, right, to appear as anomalous.
Yes. Mm-hmm. But overall, pretty good.
Perfect.
Pretty
Awesome.
good.
So now I've shown all this reconstruction. Oh, wait, no, there's one more reconstruction plot. I think it's the best one. If you could please scroll down. I forget. This is. Oh, this is about to get good. Oh, yeah, this is awesome.
HR
So now
diagram?
some fun astronomy. Now we're back to astronomy.
Oh, okay.
This is everyone's favorite, the HR diagram or the observationalist HR diagram.
Okay.
But the right is, I like to say this as a joke, but it is real, and it's an AI generated HR diagram, but it's scientifically meaningful.
Yes.
So I think a lot of people say AI generated, it's not meaningful, but in this case it is.
Okay.
And so basically what we want to see is stellar evolution versus how well it's reconstructing, right? Based on specific populations. Right?
Mm-hmm.
If you just look at the latent space and the distance luminosity degeneracy is not removed.
Mm-hmm.
You're a little clueless of what's going on.
Mm-hmm.
Where it takes a lot of work in order to get to that understanding. As to
Right.
here, again, this is one of the big advantages of having one of your subsets being labeled, right? Is we're able to do this.
Yes.
The important part is that even regions in which there are very few stars, the model is reconstructing very well, which is what we want, right? So like the white dwarfs and like even the populations of potential UV bright stars in the top left.
Okay. Yes. Yes.
Is that the figure looks almost 1-to-1.
Almost.
But if you do look very carefully, you can see that it's not the same, and you will be able to detect these guys as anomalies,
Right.
which we will see later.
Yes. Okay.
Awesome. So I have shown all of um, the model's reconstructions, right? How well it is at reconstructing all of the colors,
Yes.
right, in different populations by using this HR diagram. And it's to show the reader that they should trust the latent space that we get, right? Now it's time to really deep dive into this latent space and see what the model is doing in order to make such great reconstructions of the data.
Okay. Okay. So we'll drill down into the latent space.
Perfect. Now we're going to the latent space.
Okay. I'm with you.
So this first figure is just colored by the different magnitudes. It's just a latent space, colored by the different magnitudes, and
One broadband.
and one color. And so you get very, very nice gradients in apparent magnitude and color, which means you have a clear distinction. And these are near orthogonal to each other. This is a very important, is that it's making a very clear gradient in the apparent brightness of a star and, say, the temperature of a star.
Okay. Sure.
Awesome. And then, so if you could please go to figure 10, this
Sure.
is where we get to our globular clusters. So this is,
Oh, GCs. Okay.
yes, this is the good stuff. Awesome.
Okay. Let's blow that up a bit. Okay.
Perfect. So we've removed the distance luminosity degeneracy, right? And we can clearly see
Okay.
that the structure of these clusters is preserved, right? And so you have a clear gradient in the apparent brightness or the brightness of the stars, right?
Yes.
In the temperature of these stars.
Okay.
Um,
Okay.
and that is the important thing to show in this figure.
Okay. All GCs. Okay.
And unfortunately, NGC 4147 is a little wimpy, but M3 made up for
MP clusters are okay.
it. Awesome. But yeah, so this is one of the examples of using a subset, right, to further understand the
Right.
latent space.
Yes.
But it is not as informative of what we're going to see next,
Okay.
which is the figure right next to it, right, which is actual labels
Okay.
imposed over the latent space.
Uh-huh.
And so I start all categories, and then we put them in these subcategories, and that's what happens in the bottom and the right figures.
I'm with you. Yes.
And what you see is it's putting a lot of populations in very distinct strips, which is what we would expect, because the gradients in which you are seeing these strips being made are apparent magnitude. So if you take an object that has like quite a constant luminosity, like you took
Okay.
an RA Lyrae.
For
Did I pronounce
example.
that wrong? I hope not.
Or
But
like,
if you look at that strip, because they have that constant brightness, is that strip that you see there would be due to distance. That's a distance,
okay.
right? I mean, it's but for other populations, it's not necessarily the case. And if you scroll, I'm trying to find, yes, like the compact objects, like the white dwarfs are ranging quite a big
Yes.
range. But on the right to the left of it, you see the very clear distinction between
Oh yeah.
your helium core, your main sequence, your RGB, and your brown dwarfs. I just threw in the brown dwarfs because they're pretty cool.
They are. Ha ha ha.
And so, yeah, I I lost my train of thought, which is
You'll get it back.
the
I'll
unfortunate part.
admire the beauty of these figures while you get your train of thought back.
Okay, thank you. But it's that very, the model is very clearly distinguishing the populations,
Right.
right? And that's what we want to see. But I got my train of thought back. It's with the blue stragglers.
Okay.
So in that main thing was that you see the blue stragglers are so like beautifully in their own strip,
Yep.
like away from the rest of the stars in the main thing. And I want to note to listeners that this is an important thing to be careful about, is that this needs further study, like to see, okay, are we actually distinguishing, like, can we separate very well the blue stragglers from the main sequence stars? Or is, because we grabbed this from Sinbad, is this just a result of the paper that labeled these as blue stragglers?
Right. I'm gonna say where these labels come from. Okay.
Exactly. So it requires future study in that.
Got it.
Before saying something like, oh, it can distinguish blue stragglers and main sequence stars very well.
Gotcha.
But just to be careful.
Even got some Delta Scooties in there. All right.
Yeah.
Very cool.
Awesome.
It's doing its job. All right. Oh, here we go. Sinbad. Yeah. Okay.
Oh, yes, this is cool. So you see the RGB stars, the red giant branch stars.
Yes.
And for some reason, there's like that little branch on the right side.
Right over here.
And so what that actually is the red giant branch. That's Leo 2. So if you go down to the next figure.
Okay. Let's go down. Here we go. Ta-da.
Ta-da! Yep. So yeah, so it's just Leo 2 members. And so this also shows that you could use this latent space for like clustering techniques.
Yes. Right, because we got it there and we got it here. Right.
Yes.
Very good. I'm with you. All right. Okay.
Perfect. So now I think we're getting into anomaly detection. This is fun stuff. Figure, if you could please go to figure 13.
13. Okay, 13 is going to be
no, this is still the latent space. Let's got a little ahead of myself.
15 is when we get to the
yeah.
anomaly.
And so this is again using the subsets that we have to further understand the latent space.
Okay.
And so these two figures here, I won't go into extreme detail because it's already 1:11. Oh my goodness.
Time flies when you're having fun, doesn't it?
Yes. Just coloring it by absolute magnitude, right? You see the different populations. And if you scroll down for distance, it's like the same thing as you can make claims about the populations of stars in the latent space. Like you look at 0 to 0.5, those low mass disk stars, right, dominating the data set. And then as you go further and further and further, then you. But yes. But
I'm with you. Yes.
Anomaly detection now. I'm going to try to speed through this now for you. I don't want to.
Okay. So anomalies, figure 15, color plots. Okay.
Perfect. So on the left side, we have all stars. On the right side, we have anomalies for two different color plots.
Okay.
And so to be very vague, I will say nothing about what any of these populations are.
All right.
I just want to highlight that. Well, if you look at the right is very clearly grabbing very distinct populations, right? If you look at like the top left of G minus R versus R minus I, it's grabbing that little branch up there. And then if you look at I minus Z versus R minus I, you can see it's grabbing those little clumps at the very top left.
Right.
And that strip that you don't even see.
Yeah. Right.
Yeah, that smaller strip that's above the longer one.
Right here. I'm with you.
Awesome. So it shows that we are actually grabbing interesting objects in our data set.
And they're
without saying what the
appropriately,
populations are.
yeah, because we don't, they're weird. But they're also appropriately down by number by, several orders of magnitude here, right? Stars appear in 10 to the
Oh,
4th,
yes,
3.
yes.
We're down here
Thank you for
at
pointing that
10,
out.
which
10, yeah.
which gets to your distributions you were talking about earlier, the ones on the edges, both left and right. Those were anomalies in the 10 range. So right. I'm with you.
Awesome. Figure 16, please.
Very cool. Okay.
Thank you, by the way, for scrolling through all these figures for me.
Oh yeah.
Greatly appreciated.
Okay. Ooh, what we got here? Oh, PS1 images. Okay.
Awesome. So
Okay.
again, this is using our resources that we have available to us to make the most understanding
Okay.
of what the model is doing. And so we're grabbing pan-STARRS images of the anomalies. And so this is just a subset grab.
Sure.
But all of them are in the appendix. We threw all of those bad boys into the appendix, so you
Very
can look at
good.
all of them.
Lovely figures, by the way. People check them out.
And so I'm just highlighting a bunch of different SED shapes that the model is capturing as anomalous. And some are very clearly what's going on, right? It's very unphysical. Like if you look at the very blue one, that's going like this, that's not what's going on there. And so this highlights the importance of we are not to the point yet in which we are saying, oh, we are only grabbing anomalies that are like actually physically interesting, right? Where it's physical properties that are affecting the spectral energy distribution in a way that's weird.
Right.
It can also be observational artifacts, right?
Possibly. So they're begging for follow-up.
Yes, they are begging for follow-up, is the big idea. But it's also very important in that you can also scroll down one to the next feed. I'll show that very quickly. With the anomalies on the HR diagram, is that what I said earlier, the white dwarfs, right? The hottest objects are being grabbed as anomalies. That makes sense. Because they have the most extreme colors. But an important part is all the stars that are just inside, right?
Yeah.
And also I showed these two because it shows that a lot of the portion of the data set is not labeled, right? They don't have labels.
Right. And some you do, and okay.
And it's to show that even if we are not, the anomalies that we are grabbing are just due to observational artifacts, right? These stars still got past all of our cuts of all of the flag cuts that we made and things like that. So it is still important in to say like deploying such a model in a pipeline to even get a cleaner data set out, right? Of removing anomalies that are not physical.
Or taking another look at them, let's put it that way.
Okay.
Right. And here's a great way of showing binaries here, right? Stars.
Yes. Oh yeah, so this is getting back to it, is the figure 17 is I'm showing the Sinbad labels and the anomaly percentage for a specific classification. And this is the big point from this figure is that besides really the brown dwarfs are like the guys that are ruining my point. Is that it's not that a single population of stars are just, they're all gonna be anomalous.
Sure, everyone will be some weirdos. Okay.
There's like, if you look at
a
good example maybe would be the blue stragglers, right? Is like, what is that, 15% are anomalous, right? It's a very small subset.
257.
And so I just wanted to show in this plot that not entire populations of like very similar SED shapes, they're not being reconstructed well. And so they need future analysis to look into to see if these are actually physically interesting or if it's just an observational artifact.
Okay. Okay. Cool. I'm with you. Okay, so that's 18.
Yeah, sorry, there's a lot of figures.
20 odd, yeah.
Awesome.
Okay, so we got SED shapes and the predictions. Okay, back out.
Yes. So this is basically taking subsets of our HR diagram that we had,
Yeah.
and me showing the plots that my very first figure that I showed, in relevance to that, to connect everything together.
Correct. I'm with you.
And the figure 19 is a very basic example where it's very clear it's very easy to separate these two SED shapes.
Sure.
Except that one hot and bright star. But that star, I looked into, and it's beyond an order magnitude beyond the bright limits, the conservative bright limits.
Okay. Oh, okay.
Yes. So we think that that photometry is not accurate.
Okay.
But anyways,
Possible. Okay.
wanting to show in figure 20 is that using the M minus M prime, right? The reconstruction metric to distinguish populations.
Yeah.
In that the model is over predicting and under predicting magnitudes in very specific ways in which we can use to separate populations.
Good.
Okay. So for example, if you just look at G, if you look at that orange and that like kind of brownish one.
Yep.
And then if you scroll up to the top part of the plot, if you look from Z to Y of the orange one.
Okay.
And then look at that brown one.
Oh,
they make the same exact shape. Right. So now you're using one variable, which is G minus G prime, to distinguish that that SED shape from others.
Okay.
Rather than using multiple colors.
Yes. Right. Cool. Very nice.
Awesome. So we've gone through all the figures. We did it.
Very cool. Very cool. And thanking the anonymous referee. Always a good thing to do in your articles, people. Always a good thing to do. Very cool. Bradley and Katie, I want to thank you so much for walking us through your very awesome article. Beautiful. Okay, let's see. You mentioned it a couple of times. Hopefully my mouse battery doesn't die as we went on through. And so let me go ahead and ask it this way. And where do you think we go from here, given the published article? Is there, you mentioned some follow-up of some anomalies, or is there, you specifically chose a simplified data set to sort of get a proof of principle here? What would maybe some of the next steps be to apply this to a less ideal sample? So let's say something coming from Roman or LSST or so on like that. Is there some theoretical work that could be done, and so on? So where do you think we go from here, given the published article?
Yes. So there are a lot of avenues. And Katie and I and Christian, all three of us have talked about this. There's so many avenues to go down.
Okay.
But what I'm focused on right now is basically this was a proof of concept paper, and I really want to apply this to pan stars. And so now I'm extending this. I'm down to galactic latitude 20, and so it's about 50 million sources now, right? So, and to look at a lot of other things of like the effects of reddening more, and things like that, and specifically the idea that the model is able to freely explore the data and that you have the ability to potentially find new types of stars, rare types of stars.
Okay.
Or even do things like, say, use SCSS, for example, to try to distinguish helium-rich atmospheres and white dwarfs from
Uh-huh.
hydrogen-rich, right?
Uh-huh. Huh.
Katie, you can
DADBs.
correct me if I'm wrong about that, but those are the two.
DADBs. Uh-huh. Yeah.
And I
Yes.
want to see the U band and take a look at metallicity as well. I think
Ooh,
that's
there
a
you
really
go.
critical step.
Yes. Good. Okay. Makes sense. Very cool. Well, it's going to be really exciting to see this develop over the next couple of years as you apply this to ever more non-ideal data streams, and see the algorithm will develop as well, of course. So it'll be very cool. It's very exciting to see.
Awesome. Thank you so much.
Good. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.